All right. It's 1 o'clock by my clock, so we'll get started here. Thank you all for joining. My name is JC Arènes. I'm Vice President of Sales and Service with Novatech. We are a Canadian company specialized in distribution and integration of analytical instrumentation, everything from gas detection and flame detection, which is the topic of today's presentation, all the way up to gas analysis, liquid analysis, mass spectrometers, GCs, et cetera, and everything in between. We've been doing that now for almost 40 years. Next year will mark our 40-year anniversary, and we serve pretty much all industries across Canada with our products and services. So very quickly, a little bit of housekeeping to begin. Participants are automatically muted by my colleague, Gata, who's looking after the chat, and et cetera. So if you do have questions throughout the presentation, we encourage you to write them in the chat. If we have time at the end, we may be able to have a little bit of a question period, but I'll do my best to answer those questions certainly at the end, or if Gata raises her hand as we go along. And as you've probably already seen, the webinar is being recorded. You'll get access to a link to watch the recording after the webinar is concluded. So let's begin. Very quickly, this is what I plan on covering in today's presentation. The focus will primarily be on the technologies and system architecture that we look at for these types of systems, but I will very briefly do an introduction on gas detection and what it's for, what its purpose is, which seems pretty obvious, but does present a few interesting questions we have to consider when we're looking at this type of system. Very brief history, which of course, as it is with most things that mankind does, is horrible and terrible. We've done horrible things. We're very good at doing those horrible things, it seems, as a race. So let's get into it. What's it for? Gas detection and in consequence flame detection as well really is all about identifying hazardous atmospheres. And a definition of a hazardous atmosphere is one which meets any one of these criteria, or sometimes it could be a combination of these criteria. We're talking about flammable gases or vapors, which exceed a certain level, and we'll talk about those levels in a future slide. Oxygen levels that are potentially outside of our normal comfort zone, so the areas where humans require oxygen levels to be to exist and to function, and the presence of hazardous substances, which we might label generally as toxins or asphyxiants. There are categories of hazardous atmospheres that exist because of the presence of dusts, but even things such as very high temperatures or pressures can also be identified as hazardous atmospheres. For the purposes of today's presentation, we're really focusing on the first three. And these hazardous atmospheres can exist in most industrial environments. In fact, sometimes not even industrial environments. A classic example is if you're familiar with the stores, the store chain called Costco. They have these huge refrigerated and freezer sections. They have gas detection there. They have gas detection because leaks of those refrigerants, those freons and things of that nature, can present or create an atmosphere which would be hazardous to humans. So it doesn't necessarily just come in hazardous in industrial environments, but certainly we are definitely familiar with it when we think about environments like refining and petrochemical, where flammable gases may be present. Water and wastewater, where we may have the presence of course, flammable gases, but also toxins like chlorine or H2S, et cetera. So they can exist just about everywhere. And so gas detection and or flame detection is applicable in many, many environments. Again, for the purposes of today's discussion, we're going to focus on the three categories, which we generally group as toxic gases, combustible gases, and asphyxiants. Some examples of the types of gases that you might find depending on the industry. Toxic gases exist, again, in many more industries than the flammable gases, such as pulp and paper, food and beverage, et cetera. But combustible gases, of course, can exist, combustibles and toxic can exist in the same industries. Refining is a perfect example where you may have flammable gases and toxic gases present at the same time or in close proximity to one another. It's important to think about toxicity and its effect on people because often, especially when we're talking about hydrocarbon industries, our focus is primarily on flammable gases. And we think of that hazard first and foremost. But we do have to pause and think a little bit about what else might be present. As an example, if you're dealing with some kind of sample, a crude, for example, crude oil, or a sour gas of some kind, the effects, or the toxicity effects of the H2S, which may be present in that sample, will be a problem long before we reach flammability limits. When we're talking about hydrogen sulfide, concentrations in the tens to hundreds of parts per million can cause problems. And in fact, beyond 500 parts per million can prove fatal. So these are relatively low concentrations when you think about the fact that when we talk about flammability limits, we're usually talking about percent levels, uh, 3, 4, 5%, maybe even more, depending on the nature of the hydrocarbon. These concentrations of H2S may occur long before we reach flammability limits. So it's really important to think about the type of hazards which might be present in any given environment and what is the best risk mitigation strategy. What are the hazards that we should identify first? Possibly it's a combination of multiple hazards. And speaking about flammable gases, it's important to understand the terminology. We're very good at using three-letter acronyms in the industry. So here's another one: LEL, lower explosive limit. You may sometimes hear lower flammability limit as well. They tend to be used interchangeably, but they really define the concentration at which this combustion triangle that we're all familiar with can actually occur. For combustion to occur, which is an oxidation reaction, we need some type of fuel, something that we burn. We obviously need oxygen, and we need some sort of source of ignition. If we don't have those three components in the right ratios and the right combination, combustion doesn't happen. So if I don't have enough fuel, I'm below the lower explosive or lower flammability limit. If I don't have enough oxygen present, that means I am fuel rich and I'm beyond what's known as the upper explosive limit or upper flammability limit. Combustion can only occur between those concentrations, between the LEL, which is here, and the upper explosive limit, which is here. So only in this yellow zone that we've identified in this chart here. Now that varies depending on the molecule that we're dealing with. In the case of methane, CH4, the LEL, or the concentration at which combustion can occur, is 5%. If I have less than 5% methane in my atmosphere, I don't have enough to support combustion. With hydrogen, it's 4%. So we tend not to talk about combustible gases or the detection of combustible gases in terms of absolute concentrations. We tend to talk about them in terms of a percentage of their LEL. How close am I to reaching the combustion point with this specific hazard? So when we talk about LEL gas detectors, we're talking about gas detectors that are meant to operate in this green zone. We never want to reach this orange or yellow zone here. So we will set alarms as a function of LEL. Maybe it's 50% LEL, maybe it's 60% LEL, but these alarms would then trigger some kind of action, whether it's evacuation or shutting off valves or whatever it may be. Okay, a very brief history of gas detection and how we got to where we are today, because I find this kind of stuff fascinating. Really, gas detection was driven out of the Industrial Revolution. And if you think about the Industrial Revolution, it really was driven by the fact that we could generate power. We could generate power through the form of steam and later on through the form of electricity. But it's that mechanization or development of machines to do the work that humans used to do in the past that drove the demand for the fuel source, and the fuel source primarily of the Industrial Revolution was coal. Coal mining is a very hazardous and difficult process. You know, we faced hazards such as exhaustion, of course, tunnel collapses, but there was also the hazards due to the presence of hazardous gases. And methane was one of the gases that might exist in these coal mines. And the earliest detection methods were quite horrific, really. A volunteer, and I use my air quotes here, would be sent down into the mine holding a lit wick or torch of some kind covered in a wet blanket. And the idea was that if there were any pockets of methane, one of two things would happen. It would burn off and dissipate, or worst case scenario, you might actually cause an explosion of some kind, and the poor volunteer may not make it out of it. But these were the primitive methods that were originally used, which seem horrific today, but you know, the concept was not so much about personnel protection as much as it was about asset protection. Keep my mine running. Later on, we evolved, in quotation marks again, to develop, to use techniques that were a little bit more sensitive. And it's not a myth. It was absolutely true that miners would take canaries down into the mines with them. The canaries had the ability to detect non-standard conditions much more easily than humans could. And based on monitoring their behavior or their reaction in the cage, the miners learned to understand what was potentially present in terms of hazards within the mines. Not very sophisticated, certainly not specific, and hard to calibrate a canary. Really, the dawn of what I would call instrumentation for gas detection was the development of the Davy lamp. And the Davy lamp was really very clever. It relied on the fact that oxidation, in this case of the flame within the wick within the lamp itself, was influenced by the environment that it was being conducted in. So the process was the lamp would be lit outside of the mine in what was considered a clean environment where hazardous gases shouldn't be present. The height of the flame would be adjusted to reach the middle line on this marked case. And then as the miners went down into underground, they would monitor the height of the flame. If the flame started to grow and reach the top line, that would indicate that there was a combustible gas present in the mine and tell them to get the heck out of there. If the flame started to go down to the lower line, that would indicate that something else was present, potentially not a combustible gas, but something else that was suppressing the level of oxygen within the mine. And it could have been something like carbon monoxide. It could have been H2S. You would think carbon monoxide would lift the flame as well, but these were early primitive methods of detecting hazards and pseudo-quantifying them to some degree. The modern era, of course, came out in the 1920s, so relatively recent technology, and two kind of developments that occurred within a few years of each other. Riken Keiki company, which later evolved into RKI Instruments, found a method of detecting combustible gases by monitoring light wave interference. And very almost concurrently, the Standard Oil Company, which later became Exxon, one of the scientists there or researchers there had developed what eventually became known as the catalytic bead detector. And we'll talk about these technologies in a few minutes, but these are technologies that continue to exist today, of course, refined and updated, but we still use these for gas detection purposes today. Okay, so let's talk about the techniques and the actual technologies that are used, and this is really going to be the focus of the presentation today. We'll look at we'll look at it by hazard and hazard type. There is a little bit of overlap. Some techniques can be used for both the detection of toxic gases and combustible gases, primarily infrared, but mostly they tend to live apart. So if you see the list of toxic gas technologies, electrochemical, metal oxide semiconductor, PID colorimetry, They don't exist on the combustible side. And likewise, on the combustible gas side, catalytic bead detection and H2 scan, which is a very specific one, does not exist on the toxic gas side. So let's go through them. And the order is somewhat in terms of increasing complexity, if I can say that, though it's not necessarily true all the time. Let's start with electrochemical sensors. And this is probably going to be the most common technique that exists out there in the market today. The reason I can say that is that what we saw earlier in terms of industries or environments in which gas detection is used, yes, of course, refining, petrochemical, hydrocarbon industries, big users of gas detection, but so many other industries use gas detection as well. And they are primarily looking for toxic gases. And so this is the world of the electrochemical sensor. They've been around since the 1950s. The concept of an electrochemical sensor is actually pretty basic. I think the analogy I use is it's like a battery. It's like an energizer battery type thing that's missing one component in order to operate. So what you have is a container or reservoir of some kind that has an electrolyte and an anode and an electrode of specific metallurgy, and the electrolyte is of a specific chemistry as well. And they're designed in such a way, or chosen, the materials are chosen such that if a certain gas is present in the atmosphere, when it diffuses into the electrolyte, it will allow current to be generated. And it's proportional to the amount of gas that exists in the atmosphere. So if, for example, I have an electrochemical sensor designed for the measurement of hydrogen sulfide or H2S, if H2S is present in the gas phase, it will want to reach an equilibrium with the H2S that exists in the liquid phase of the electrolyte. And as that concentration increases, the current I generate increases as well. If I take the H2S out of the gas phase, the H2S in the liquid phase will want to come out, and therefore I will generate less electricity. So the amount of current that is generated is proportional to the concentration of H2S in the atmosphere. Now they're primarily used for toxic gases and oxygen, also for refrigerants, and the one exception, or the one that overlaps both, would be hydrogen. We can use electrochemical sensors for hydrogen detection as well. They do have limitations, however. It is a chemical reaction that is occurring. You are basically transferring electrons from one electrode to another electrode. You have buildup of material on one and degradation of material on the other. There's the risk that the electrolyte may become contaminated and consumed over time. All of these things mean that the performance day one is not the same as the performance day 100 or 1 year down the line, and therefore calibration is a must. Most manufacturers recommend that electrochemical sensors be calibrated quarterly. A lot of the formulations of electrochemical sensors require oxygen. There are some types of EChem sensors that work without oxygen being present, but you'd have to check with the manufacturer of your specific sensor whether or not that is the case. Why is that important? Well, a number of reasons. You may be looking for a hazard that exists perhaps in a storage room or a storage locker or in a sump or something of that nature. And another gas may come along that you're not searching for, not detecting, that could suppress the oxygen in that environment. And now your sensor is no longer functional. So it's something to absolutely take into consideration. They have a finite life. As I mentioned earlier, that reaction that is occurring means that the sensor is degrading over time, and we calibrate to compensate, but eventually you get to the point where you can no longer compensate for it. The sensor has to be replaced with a new one. Fail to zero is certainly a problem, or was a problem with these technologies. The analogy is, if the gas is not present, it generates no current. But if the sensor has failed, it also generates no current. Do I know the difference between the two of them? And in the past, when all of our gas detection systems tend to be fully analog in nature, The only way to know was to actually apply gas to the sensor and test it and see what was happening. As manufacturers are migrating to digital technologies, they have some ability to actually monitor the health of the sensor. It's not foolproof. There are still scenarios where a sensor could fail potentially. So that is something to keep in mind and be aware of. It's the reason why, whilst you may only have to calibrate quarterly, bump testing is still something that should happen on a more frequent basis, monthly, perhaps even weekly, depending on the nature of the hazard. And electrochemical sensors are not super specific. They tend to react to uh, families of gases. It might be mineral acids or things of that nature. So there are often situations where they can be cross interferences. Generally speaking, those are well understood and well known, and you can deal with it and know how to handle that type of situation. But it's important to pay attention to it. Infrared sensors rely on the fact that gases will absorb energy at certain specific wavelengths based on their molecular structure. And if we know that, we can use that to quantify the presence of a gas based on its absorption of infrared energy at the wavelength of interest. So the way these sensors are set up is they will use usually a broadband infrared source. So it's think of it as a light bulb that's emitting energy across an entire spectrum of wavelengths. We transmit that energy through our sample, and our sample is basically just an open area of the detector where the air can migrate in and interact with that infrared energy. And then we have an optical splitter that will send a portion of the energy to one detector, which has filters to look at only a reference wavelength, and another detector, which has filters to look only at a measurement wavelength. The measurement wavelength, of course, is the wavelength at which we know interference can occur or absorption can occur. The reference wavelength is a wavelength chosen because it should not absorb energy. And that allows us to compensate for things like fouling of the windows, degradation of the lamp, etc. So the concept is if the two signals are decreasing at the same rate, then it's not due to gas being present. If the measurement signal is decreasing at a rate greater than the reference wavelength, then that is proportional to the concentration of gas that's present in the atmosphere. What do we know about, or what do we like about infrared sensors? Well, they're fast. Generally speaking, once the gas gets into this window, the reaction is instantaneous. It isn't a chemical reaction. We're not altering the gas in any way like we were with the electrochemical sensor, where it had to be absorbed into the liquid, allowed some reaction to occur. None of that is happening here. We're just interacting with electromagnetic energy. So it's very quick, there's no reaction. And because there's no reaction occurring, it's a more stable technology. We don't have to compensate for the fact that my electrolyte is decaying or something like that. They are fail safe. My zero signal is when I have the most energy. So that they don't fail to zero like electrochemical sensors might do. They generally are more stable. Calibration is less frequent. Uh, and because of the type of wavelengths that we look at in the infrared spectrum, they are primarily used for hydrocarbons. So anything that has the carbon-hydrogen bond, methane, ethane, propane, things of that nature. Generally speaking, not very, very large molecules. Once the molecules get larger, the interactions with the infrared spectrum become much more difficult to manage. So smaller infrared molecule, or sorry, hydrocarbon molecules and carbon dioxide. There's a variation on an infrared sensor, which is called a dual beam, sometimes also called dual beam, dual compensation, which just takes it one step further. Instead of having a single lamp, it has two lamps and two detectors. Each detector is checking both lamps. So there's always a compensation for decay, which means that these types of setups are actually even more stable. Some manufacturers will claim that these types of detectors never need to be calibrated. Very useful for applications where maybe There's not a lot of trained personnel or skilled personnel available to maintain the detectors, or perhaps are located in an environment which is difficult to access. This type of setup this type of technology can be very useful. But they do have limitations, as all of them do. They do tend to be a little bit more expensive than the other technologies. They do not detect hydrogen. So while infrared is commonly used for flammable gas detection, it's flammable hydrocarbon detection. It will not detect hydrogen. Hydrogen does not absorb in the infrared spectrum the way these do. They can be too specific. There are environments or situations where you may have a multitude of different flammable gases present, that may change over time. So perhaps it's a batch processing facility, maybe it's a printing process where different solvents are used or something of that nature. And we need something that's a little bit more generic, that will just detect a flammable gas as opposed to detecting this specific flammable gas when some others might be present. And depending on the design of the sensor, if we do get fouling of the windows, if it's depending on the way it's configured, they may not be serviceable. It may be a situation that once the sensor is fouled, it simply needs to be replaced. Typically, the larger, the dual beam, dual compensation detectors are set up in such a way that you can actually open it up, take it apart, and clean the surfaces and deal with that. Catalytic bead sensors, back to the invention of Dr. Johnstone at what was back then Standard Oil, which is now Exxon. These continue to be one of the most, if not the most popular form of combustible gas detector. The concept is that of a balanced Wheatstone bridge that has two filaments on it. Little wires that are coated within either a ceramic or a glass bead of some kind, or embedded, I should say. One of the beads will have a catalyst on it and the other does not. And the idea is that as we're passing current through them, we're heating up these beads. And because we're operating below LEL, right, we're not at the point where combustion can occur. On the uncoated bead, nothing happens. There's not enough of the methane or whatever hydrocarbon we're looking for to actually support combustion. But on the catalyst coated bead, it will allow combustion. Catalysts lower the energy requirement, allow reactions to occur in circumstances that would not normally allow that reaction to occur. So we do get combustion happening on the catalyst coated bead. Because we have combustion happening, we generate heat. Combustion or oxidation is an exothermic reaction, which means that the temperature of that bead changes, which means the resistance of that bead changes. So you get an imbalance in that electrical circuit, and that imbalance is proportional to the amount of combustible gas that's present in the atmosphere. So very interesting in the sense that these types of sensors will react to anything combustible, whether it's a hydrocarbon, whether it's hydrogen, whether it's carbon monoxide, anything that is combustible will react in a catalytic bead sensor, which is a pro or a con potentially. So back to what I'm saying, they're non-specific, react to anything combustible. Of course, it's combustion that's occurring. If I don't have oxygen in my atmosphere, combustion or oxidation cannot occur. So they must have oxygen present in the atmosphere in order to operate. So back to our example earlier where we talked about maybe an enclosed space or an enclosed environment or a sump where something may accumulate because of a leak or something of that nature. If that accumulation displaces the oxygen, the catalytic bead detector won't react, but an infrared sensor might. Now, there's a reaction happening. We are oxidizing the sample, which means that this changes over time. The response today is not the same as when the sensor was new. It degrades over time, therefore calibration must occur, and they can be poisoned. There are some substances, chlorine, silicones, some acid gases, which will actually poison the catalyst and reduce its ability to oxidize the sample. And finally, they will fail to zero, but again, this is a limitation that speaks more to the old analog technologies that existed in the past, and you could potentially detect an open circuit. Certainly modern detectors will. Photoionization detectors, or PIDs, are a technology that's primarily used for volatile organic carbons. They use a UV lamp to basically ionize any molecules that migrate into the chamber, and those ionized molecules will allow a current to flow between two electrodes within that space. There are specific or certain types of molecules that will be ionized by the UV lamp, so it doesn't occur for everything, but the volatile organic compounds in particular react well to this technology. What's interesting about it is that depending on the ionization potential of the lamp, UV lamp, that is fitted to it, certain molecules can be ionized, others cannot. So if, for example, I have a 10.7 electron volt lamp fitted to my PID sensor, everything to the left, so in the orange and in the red section, is detectable, but things to the right are not. So that is good and bad. It's good from the standpoint that it will detect VOCs. It's bad from the standpoint that it is non-specific. If you need to specifically know how much heptane is present, then and there may be other VOCs present in the atmosphere, this isn't going to give you that result. It'll give you a result which is a function of all of the VOCs that are present. UV lamps have a finite life. They do tend to degrade over time. And just like any kind of technology where there could be contamination of the windows, like in the infrared sensors, these sensors will also be affected by that. If you have a coating that covers the aperture where the UV light is emitting energy into the sensor, then that's going to decrease its ability to do so. Metal oxide semiconductor sensors were kind of a reaction to a problem that existed in certain specific environments. They're known as thin film sensors. And the idea is that certain molecules will interact with this film and change its electrical properties. And they're particularly used for H2S monitoring. The advantage of metal oxide semiconductor sensors over traditional electrochemical sensors is that you don't have a liquid electrolyte present. And therefore, in very dry environments, such as the Middle East, or very cold environments of that nature, they can potentially be a little bit more resistant to some of the effects that the atmosphere can have on the EChem sensors. However, it's not all rosy. They do have a warm-up time. It can be as long as 48 hours. So, when you think about that from a logistics perspective, you come, you install a sensor, you go away, you come back 2 days later to calibrate it. That's a big deal if you're having to do that on site. They don't have a linear response. They don't go down to zero. They have a curved response, and therefore they have to be calibrated at two different concentrations. Typical calibration frequency of 4 times a year. The humidity level in the calibration gas has an impact on the response of the sensor, and so therefore the cal gas should be humidified to the same level as what's present in the atmosphere. You could argue that that's also a good practice for any technology, but it's especially true for metal oxide semiconductor sensors. There were reports in the past of these types of sensors falling asleep. I'm not sure that that's nearly as big a deal as it used to be. And failing to zero isn't quite the right terminology here. It's more the falling asleep business where they don't respond potentially when there's an exposure. So MOS, suitable for certain types of applications in certain types of markets, but the EChem sensor, especially modern EChem sensors, address these limitations quite well. H2Scan, I've named as a company because they're the only company that make this type of sensor. So I figured I might as well. There's no point in hiding it. It's a little bit like the metal oxide semiconductor sensor in that it's an electrical property that is affected by the presence of a certain gas. So the H2 scan sensors are made up of a palladium nickel matrix, um, onto which hydrogen molecules will dissociate to hydrogen atoms. And those hydrogen atoms will fill some of the interstitial spaces within the matrix and change the electrical properties of that palladium nickel matrix. So depending on the range that we're trying to measure, whether it's low concentrations or if we're looking at LEL level concentrations, we're either looking at the capacitance or the resistance of that matrix. Nice thing about it is that it is specific. It will only react to hydrogen. It doesn't require oxygen to be present like the catalytic bead sensors do. It's not an oxidation reaction that's taking place. So they have some very useful features and properties that help address some of the shortcomings of the other technologies. However, they are expensive. They're not inexpensive compared to traditional gas detectors. We actually find ourselves using H2 scan more often as a process measurement as opposed to a gas detection technique, but there are applications where it may make sense to use an H2 scan. We do have to be careful of certain background gases, depending on the range we're trying to measure. Again, the difference between gas detection versus process applications, there are potentially limitations in terms of what might be present. And then colorimetry is a technique that's very used in very specific applications. The concept is it's basically a treated paper tape, a filter paper, if you will, onto which a certain coating has been applied. And that coating has been selected because it will change color when exposed to a certain type of gas. The way these analyzers or these detectors work is that they're constantly sucking a sample. They're extractive in nature. There's a pump that's always pulling a sample through. The sample literally flows through the paper. It's like a filter paper. And there's an optical setup on it where we are shining light onto the paper and looking at the light that is reflected. And as a stain develops, it will change the amount of light that gets reflected back to the detector. Huge benefit for these or for this technology is it can measure very, very low concentrations. The reason it can do that is that it doesn't use the intensity of the stain to quantify the concentration. It uses rate of change. And so therefore you can basically integrate over a period of time and are able to measure in parts per billion for certain applications. Because it's extractive in nature, there's a pump. You can imagine a scenario where you have a centrally mounted analyzer that's pulling from multiple points throughout a facility, which does make it a little bit more cost effective. It leaves evidence of gas exposure. If you have any doubts about whether or not the reading or the alarm that was triggered was due to a false alarm or anything like that, you can literally pull the tape out and look at it. And if you see a stain of a specific color, then you know that your target gas was present. And the types of applications that it is used for, and I said measures weird stuff, and that's probably the best description for it. The two that come to mind are isocyanates. Isocyanates are used in the making of foam. They're also used in some paint processes for the automotive sectors. So if you've heard of two-component clear coat, that often uses isocyanates. And they're also very good at detecting really, really scary gases in the semiconductor industry like arsine, phosphine, things that, you just mention it and it kills you basically. Those types of gases down in parts per billion levels, this is where these things shine. However, again, like everything, they have limitations. They're more expensive to purchase up front. We're verging on analyzer pricing here as opposed to gas detector pricing, and the tapes are consumable. The tapes get used up, and once you've used it, it's a throwaway item. You have to replace it with a new tape. The other thing to keep in mind is that we're looking for the development of some kind of stain. Lots of things can create a stain, including dust and smoke. So if the environment, if welding is happening just down the lane from where this detector is set up, it will draw in the smoke from the welding process, and the instrument won't know the difference between a smoke stain versus a gas stain, and could trigger an alarm. Everything that I've described up until now has been what we would qualify as point gas detectors. It's a detector either that is mounted at the point where we want to detect the presence of a hazardous gas, uh, or potentially can bring samples from points. The next evolution or the next stage is what we call open path. And the idea with that is, well, I like how these infrared gas detectors work, but it's only measuring in this spot right here. What if I separate my lamp and my detector by meters, potentially hundreds of meters, and I look at what happens anywhere along that line of sight between my lamp and my detector? And that's the concept of open path gas detectors. They are primarily used for hydrocarbon leak detection, but they are also used sometimes for toxic gases, H2S in particular. There's a bit of an evolution that came out. Really, these things came out in the 1980s, but what I would define as the modern era of open path gas detection is from the mid to late 90s, when we started using things like xenon flash lamps and things of that nature. Much more robust, the ability to monitor over, again, potentially hundreds of meters in distance, much more intelligence in terms of signal, bad signal rejection and things of that nature. But it's not all roses. There are some challenges with open path. Obviously, if you get something in the path, you've got a problem. If somebody parks a truck right in front of the detector or midway or whatever it is, and the signal can't get from one to the other, well, then it's not working anymore. Obviously, you've got a blocked beam. But the second part, which is really the part that most people struggle to get their head wrapped around, is quantification. When you think about the little infrared gas detector that has a path length measured, maybe 1 centimeter or something of that nature, you assume that the entire volume of that cell will be filled with a homogeneous gas mixture, and that the concentration throughout the cell is consistent. So if I have 50% LEL methane, which is 2.5% methane in air, then I assume that that's what the concentration is throughout that cell, and therefore that is the concentration at that point. With an open path gas detector, if I have these things 100 meters apart, I don't know where the cloud of gas is, and I don't know how big it is. In this example that I'm showing here, those three scenarios will give the exact same reading. I can have a 100% LEL, so 5% methane gas cloud that's 1 meter wide. That'll give me the same signal as a 50% LEL cloud that's 2 meters wide, or a 10% LEL cloud that's 10 meters wide. At 10% LEL, I'm not alarming normally, but at 100% LEL, I should be evacuating. But how do I know? You don't. And so open path gas detectors typically can't be the only solution. They tend to be used in combination with either some strategically positioned point gas detectors or some kind of strategy such that I get a signal on the open path gas detector, and the next response is to send somebody out with a sniffer and maybe try to locate the leak and quantify what that leak looks like. So they help. They can reduce the number of point gas detectors. They can do things such as fence line monitoring potentially between a facility and a neighboring property where we don't want gas clouds to migrate across, things of that nature. But they are not necessarily great at being the method by which we determine evacuation alerts or shutdowns or things of that nature. They don't give sufficient information. The output from an open path gas detector will be expressed in LEL meters. So in other words, it's the equivalent of this, the 100% LEL gas cloud in a 1 meter path length. So that's how they would operate. So limitations, obviously line of sight is required. You have to be able to shine the light from the transmitter to the receiver. Ambient conditions can be problematic, especially as we start getting to very long path lengths. If we are in an environment where fog is common, or snow or rain, those can have an impact. Even temperature, wide temperature swings, very rapid temperature swings. So very hot environment followed by a rain shower, that can cause interference potentially in some of these scenarios. And then the final point, of course, is the quantification. So no one size fits all solution for any of these. There's also a concept of optical gas imaging, which is really useful as a leak detection technology, in terms of at least pinpointing the location and giving us some approximation of quantification. The way these work is basically, as opposed to having a detector and a receiver and we're looking for infrared absorption, we are now effectively looking at um, disruption of thermal, or basically radiometric signals. So surfaces that have a certain temperature, when a leak occurs, will have a very rapid change in radiometric behavior or emissions. They work very much like the FLIR cameras that we're familiar with, but very sophisticated software and the ability to pinpoint, visualize, so provide an actual camera feed to the operators and show, here's your leak, it's right there, and I think it's approximately this much that's leaking out. So it's clever, it's one step beyond potentially maybe addressing some of the shortcomings of open path gas detectors. But again, line of sight, if something is blocking the instrument, it's obviously not going to work. Limitations again with sensitivity due to ambient conditions. If we have heavy rain coming down on surfaces, it tends to equalize all of the temperatures. So the system may not work until things warm up again potentially. And again, quantification, it's an approximation. It's not a true number necessarily. So those are the techniques that are used for detecting gases. But we also have to keep in mind that sometimes we need to detect something that's already gone wrong. Gas detection, the intention is to predict or prevent things from reaching a problem state, whether it's a toxic or flammable gas or an asphyxiant of some kind. Flame detection is, hey, okay, it's already progressed, but you might not even know that it's happened, and I'm going to tell you that you've got a problem. So an optical flame detector is designed to detect any kind of open flame and trigger a response, of course, and give you information about where the problem is, the nature of the problem, and maybe even the size of the problem. They are a little bit like that optical gas imager in the sense that they have a conical kind of field of view, but they rely on a different principle altogether. Science, Kirchhoff's laws, molecules will absorb energy, cold molecules will absorb energy at the same wavelengths that the hot molecule will emit energy. So if I think about something like carbon dioxide, cold carbon dioxide, like in the air, there's carbon dioxide in the air all the time, absorbs energy at certain wavelengths. If I take that CO2 molecule or CO2 gas and heat it up, because now it's product of combustion, then it will actually emit radiation at the wavelengths that it was absorbing before. So I can use that information to actually detect the presence of a fire. And it's very convenient that the products of combustion of hydrocarbons in particular are primarily water vapor and carbon dioxide. Why is that convenient? Because water vapor and carbon dioxide exist in the atmosphere all the time. So the energy that comes from the sun, the infrared energy that comes from the sun, is absorbed by the water vapor and the carbon dioxide in the atmosphere. So we get these big dips in the infrared spectrum where water vapor at 2.7 and carbon dioxide exist. So then if I have a fire that's generating water vapor and carbon dioxide and it's a hot body, we'll actually generate energy at these, or emissions at these wavelengths. And I can use that information. There's also stuff that happens in the UV region. Typically, there's not much in terms of UV energy, but we can get UV signatures from fires because of the flicker that is generated by those. So there's three areas that we can look at specifically that can help us determine if a fire is present. In terms of the ways, obviously there's lots of ways to detect fires, but as I've talked about just now, the combination of looking at the infrared spectrum, various wavelengths in the infrared, UV and infrared, or various wavelengths in the infrared, gives us the options and a number of different approaches that we can use for flame detection. And which one should you use? Well, the cop-out answer is it depends. It depends on what might be burning. So if your facility only has hydrocarbons, then potentially an infrared technology that looks at just the H2O peak and the carbon dioxide peak may be sufficient. There may be applications where you have hydrogen fires. Hydrogen fires will not generate a CO2 peak, so we may look at the water peak and the UV for that ability to detect the flicker and the generation of the water. So again, it depends, and you'd want to talk to your gas detection manufacturer, supplier, or sorry, flame detection supplier to basically qualify your specific application and which technology makes the most sense to use for that type of flame detection. So finally, we'll conclude with a few thoughts about, okay, there's all these technologies, loads of choices. Clearly, I need to talk to somebody who's got expertise in this. But how do I actually put this all together? And again, the cop-out answer is it depends. Back to what we talked about a minute ago. We have to evaluate all of our options. Are we looking at point? Are we looking at open path? Are we looking at flame detection? Are we looking at a combination of 2 or 3 of these technologies? Do we look at networked versus analog sensors? Do we look at automated response functions such as shutting off a fan, shutting a valve from a process? Do we need annunciation of some kind to give warning to our personnel so that they can safely evacuate the location? We really need to understand the drivers. Are they legal? Are they regulations? Is it a building code? Maybe it's an industry standard. What is the hazard that we're dealing with? Toxic, combustible, or both? And then all of the other factors will come into play as well. Indoors versus outdoors, wind direction, enclosed spaces, sump, ceiling. All of these things will have an impact as to where the sensors are going to be located, what type of sensors you're going to use, and what you're going to do in terms of a response to some kind of signal. Some examples of the danger points that we might consider looking at when we're talking about any kind of process environment, whether it's a refinery or anything of that nature. There are leak points that we have to be aware of: seals, flanges, gaskets, any kind of valve stems, things of that nature. There are storage areas potentially where we're actually storing some of the products that we're talking about. It might not be a tank farm in a small facility. It might even be an enclosed room or an annex to a building or something like that, where potential leaks, depending on the nature of the gas, might accumulate. It might accumulate near the floor. It might accumulate near the ceiling, but we have to be aware of what those are. Battery rooms are becoming a bigger and bigger thing. Batteries, depending on the nature of the types of batteries that are being used, can generate hydrogen oftentimes. So knowing that here we've got a thing that actually can make hydrogen, are we taking the necessary steps to monitor for the presence or the accumulation of hydrogen in this environment? Sumps are a big one. A lot of the hazards that we deal with are gases that are potentially heavier than air. They're going to want to accumulate in the lowest point possible. They'll just naturally migrate there. Wherever water accumulates, that's where your gases may accumulate as well. It's an environment where it can be very dangerous. You may send somebody down there potentially, and they might be overcome without even knowing that there was a hazard present in the first place. We may look at, from a different perspective, rather than looking at the points of release, we may look at the points where We are concerned about the gases being present, whether it's where personnel may exist, so something like an analyzer shelter, a maintenance area, a walkway. It could be that we look at things like ventilation system. So we may have a process unit over here, and its air intake for the building is downwind from the process unit. Are we pulling potentially hazardous gases into our lunchroom or something of that nature? Super important to think about those types of things. Pump rooms, again, pump rooms oftentimes are enclosed spaces, and we know pumps leak. They just do by their very nature. They will leak. So, are we creating an environment where hazardous gases can accumulate and potentially cause a problem? We have to think about what we're going to do with the information that we get. What are the response functions? Are we going to trigger a beacon and a horn? Are we going to start a fan? Are we going to shut down the process? These are drastic measures, obviously. And then we have to think about what is a realistic consideration in terms of, okay, if I have an event here and it will take 10 minutes for my personnel to get out of the area, is that enough time? Or do I have to think about detecting earlier by moving my detection points closer to the source of emission, things of that nature? Do I need redundancy? Because it's so critical that I can't rely on a single point. Maybe we'll have multiple point detectors with a voting function. In other words, trigger an alarm if 2 out of the 3 detectors in this zone sense anything above 20% LEL, things of that nature. Margin of safety, again, there may be legal requirements or specific regulations, whether they be company regulations or jurisdictional, provincial, federal, etc., that may stipulate certain actions take place. You, of course, have to think about the gas. And back to the example I used earlier, Novatech, for example, often makes sample conditioning systems for customers in the refining and petrochem industry. And if I use that example of the sour gas that we talked about earlier, and I have a sample system in an enclosed box, the natural instinct would be, well, of course, it's flammable gas. I'm going to put an LEL gas detector in there. But the hazard that's more likely to cause danger to personnel is the H2S. The H2S at 500 ppm could overcome a worker that opens the door to that cabinet and potentially knock him flat on the ground. So is an H2S detector the better approach, or a combination of both? Those types of things have to be taken into consideration. The specific gravity of the gas that we're trying to detect. Is it heavier than air? Is it lighter than air? That dictates where I'm going to set up my sensor. Rate of evaporation. Ventilation and air currents is a great one, for example, where I may have a room that is fed and exhausted by a common fan. Well, maybe the simplest approach is to put a detector at the outlet so that anything within the room that is a leak will be seen at some point, and then maybe I can go investigate where the leak is coming from. So all of this are steps and measures that one would take to really identify the specific physical, environmental, and airflow scenarios or constraints that exist within an environment. And all of those have to be used as part of the considerations in designing a gas detection or a flame detection system. And finally, just as a reference, there are publications that give guidelines or some sense of direction for how we can deal with these types of things in terms of potentially limits, practices of how to install things and things of that nature. I've left them here, and of course, you're more than welcome. We will provide the presentation for you at the end so that you can refer to these. So that is it. And boy, I've got 2 minutes left, so I think that worked out pretty well. If there are any questions, I'm looking at the chat right now. I don't see anything right now, but you're welcome. Gata, if you want to unmute the participants, if anybody's got a question, I'll be happy to answer them. No questions. When I see no questions, that tells me that my presentation was so good that I answered everybody's question. And so that's what I tell myself when I'm standing in front of the mirror. All right. Well, thank you very much, everybody. I really appreciate you joining us, and uh, feel free to reach out to me or any of your Novatech representatives for any of your gas detection or flame detection needs. Thank you.